Okay, so first we're identifying two functional groups. So first, I see I have this nitrogen atom, and I see adjacent to it, I have this carbon-oxygen double bond. And that carbon-oxygen double bond is called a carbonyl. And when I have a carbonyl with this nitrogen, this whole group is called an amide. So I definitely see an amide present. Okay, that's easy. And then I see something else. So I see this kind of six-membered ring with alternating pi and sigma bonds, but it has this extra OH. And what this extra OH is it's the phenol, okay? It's not, remember benzene, this would be, that whole thing is phenol, okay? And we talked about the origins of that name, phenol. It comes from phenyl, like, I guess I'll just write it up here, P-H-E-N-Y-L. Phenyl is another name for benzene, and then plus alcohol. So you can see phenyl plus all makes phenol, just so it helps you guys remember that, okay? So that's literally A, and you guys get, a free 4 points right there, all right? B, what is the hybridization of the nitrogen atom? Okay, so remember what we do. We have to draw on any lone pairs that aren't explicitly there, so I know that nitrogen has 1, okay, and 3 bonds associated to it. So if I were to count the areas of electron density, that would be 4 total areas, right? So we have this 1 sigma bond, this other sigma bond, this other sigma bond, and that, lone pair. So that would be, 4 areas of electron density, and we said that our exponents have to add up to 4, or the number of areas of electron density, okay? But there's always one thing you have to check, and it's like the biggest trick on exam 1 is always check for resonance. And is there resonance with this nitrogen? And yeah, there is, and you can either go 2 different directions. For me, I'm gonna go to the right, okay? And you do 1 move at a time from source to sink, unless you exceed the octet. And I definitely exceed the octet at that carbon. I have 2, 4, 6, 8 electrons there already. So I have to force these pi electrons also out, okay? So the resulting structure of this is gonna be, I'm just gonna do R for the rest of the molecule, and it looks like that, okay? So that's the resulting structure of those resonance moves. And now if I count the areas of electron density, I see that I only have 3 regions. I have this sigma bond, this double bond, and then 1 more sigma bond. So that's 3 total regions, and my powers have to add up to 3. So S1P2, and that tells me that the hybridization of the nitrogen atom is sp2. Easy. All right. So the next question is going to be, what is the electron and molecular geometry? They could be the same, they could be different, so just make sure that you are very cognizant of any resonance possible, because that's like the big indicator there. So the first thing is electron geometry, and we know electron geometry is hybridization. That's all I think about. So if sp2, we know it's trigonal planar, and that's my electron geometry. Don't even think any further. So electron geometry is trigonal planar. Okay, trigonal planar. And then molecular geometry was back to that VSEPR theory, that valence shell electron pair repulsion theory. You have to memorize those things back from Gen Chem. They're not that bad. I think there's like 7 or 8 of them. I know somebody asked me to write a list. I'll get there. I'll get you guys a list at some point. But yeah, so that's VSEPR theory. So I see I have 3 total bonds. So that's AX3, and AX3 is also trigonal planar. Okay. So double trigonal planar. Oh, good point. Which one is the carbonyl carbon? Okay, so the carbonyl carbon is this carbon. So the carbonyl is carbon-oxygen double bonds. So, this is an aldehyde, this is a ketone, and both of those have these carbonyls. So it's this kind of, and that's a very important name to know, carbonyl. It comes up like a million times in this class, carbonyl. So the carbonyl carbon would be the carbon in that group. All right.
I have a quick question about the geometries.
Sure.
When you're looking at the electron and molecular geometry, are you considering it when it's like when it's gone through resonance, or are you looking at it when it's already written there?
Yeah, great question. So you do it after resonance. It's always, everything with either hybridization or geometry, whatever it is, you always have to resonate first and then make your decision later. That's a very good question. Yeah. Anyone else? I think there's some in the chat box. Let me see what's going on here. Emily, I got yours. What is the difference between molecular and electron? Okay, so again, we said last class, electron geometry is always dealing with hybridization. So 3 types of hybridization schemes, and we'll go over them again today. but we have sp3, sp2, and sp. sp3 is always tetrahedral with 109.5 bond angles. sp2 is always trigonal planar with 120 degrees, and sp is always linear with 180 degrees. Okay, when we talk about these words, these tetrahedrals, trigonal planars, linears, that is electron geometry. Okay, and this is bond angle. Bond angle. Okay, and I'm writing this fast. So when it says electron geometry, you just look for these specific hybridization schemes and you assign either tetrahedral, trigonal planar, or linear. When it's talking about molecular, you have to go back to Gen Chem and use that Vesper theory stuff. Okay, so like AX4 is tetrahedral or AX42 is square planar, like those are the rules that you need to go back to. I think there's another chat in here. Electron geometry looks at the hybridization. Oh, thank you, you answered that. Where can we find the recorded lecture of the previous one? Roxana, is that a lecture? Oh, I don't know what you're posting, but yeah, about the previous sessions, I'm working on it every semester. It's like a huge pain to get those in there. So I will do my best to get you those. And is somebody going to say something? Somebody want to add anything? The professor provided this list. Oh, awesome. Thank you, Roxana. Everyone check out that list in the chat. There's a list that looks like, let me open it too. Yeah, perfect. Yeah, I feel like that's about right for all you need to know. AX2, AX3, AX4, AX5. Yeah, those are all good ones. Yeah, that's a great chart. Everyone look at that chart, save it or something. All right. All right, so anybody have any other questions about, you know, this apply question? Get in the habit of knowing how to do these. All right, let's jump to some more practice. So let's just jump here. So we're gonna pick up where we left off. We're gonna do E real quick. We'll talk about some key points and then we'll go to new material. So again, this kind of blends everything together, and let me fix this here. All right, hopefully that's better. Okay, so for A, we need to draw in any lone pairs that aren't explicitly drawn in, and we have 2 lone pairs. And a lot of people ask me how I know lone pairs. I think that's actually worth going over real quick. Let me just do this for you guys. I'm going to pull up a periodic table. This is a really, really good trick to help you guys like in the future. No memorization, just being smarter, I guess. Okay, so where's Zoom? Sorry, guys. Share. Oof. One sec, guys. Okay, it's actually not letting me share my screen. I have to like change my settings, so that's annoying. Can somebody share a screen of a periodic table? That'd be great, and I can just talk about it with everybody. I don't know if you guys can. Someone can. Literally anybody. I'd really appreciate it.
Sharing screen's disabled for anybody that's not the host.
Darn.
I think if you want someone to be able to share their screen, you have to make them the co-host.
Hey, Steven, it's on the back of the workbook. You just want to show it.
Oh, you know what? Good point. Thanks, Adam. All right. Here. Great point. Thank you, guys. All right, group effort. So essentially what you want to do is you are typically, we're only dealing with like 3rd row and above because, you know, that's going to be the p orbitals kind of cap off here in terms of like not having D stuff. So we're kind of only staying with the top 3 rows, right? So we know that when we're trying to figure out valence configurations, you can basically just look, you know, here's 1, so that's 1 valence electrons, 2, you know, you guys know that already. But look all the way over here. I don't know if you can see this. I did this from a last semester. But a good trick is to know that, you know, atoms that are in the same column have the same valence configuration, meaning like 4 or 5 or 6 or 7, you know, so on, types of valence electrons, which means they have the same reactivity, okay? So basically, I know that boron has 3 valence, okay? And everything below would have 3 valence, okay? So if that's 3 valence, that means just it likes 3 bonds and only 3 bonds. And then, you know, aluminum likes to go to 8, but boron's that one exception. So boron's not the best example, but C, N, O, and F and the halogens, I'm sorry if this keeps moving. Everything to the right of here, here's the trick. Carbon has 4 valence, so it likes 4 bonds. Everything in its group also wants 4 bonds, okay? So no lone pairs, okay? So see that C has 4 lines to it. It will never have lone pairs. And if it does have lone pairs, it's gonna have a formal charge associated with it, okay? Nitrogen. Nitrogen has 5 valence electrons. So you see that kind of arrangement with the 1 lone pair. In order to have 5 valence electrons, we have 1 lone pair. So everything else in this column is going to have this same kind of skeletal arrangement. If it doesn't have this arrangement, it's going to have a formal charge. Okay. Oxygen. Oxygen has 6 valence, and the way to get 6 valence is always 2 bonds and 2 lone pairs. And it could be bonded in 2 different ways. It could be 2 sigma bonds or 1 double bond. But no matter what, everything in this oxygen column is always going to have 2 lone pairs and 2 bonds. And if it doesn't, it's going to have a formal charge. Okay. Next one for the halogens have 7, and the only way to have 7 electrons is to have 6 lone pairs and 1 bond. So if it doesn't have this configuration, it's going to have some sort of formal charge associated with it. Does that make sense? So now you'll know, like, oh, how do I know that there's maybe 2 lone pairs on sulfur? Well, it's in the oxygen column. And how do I know if arsenic has, we're not going to deal with arsenic, but you know what I mean. How do I know if phosphorus has 1 lone pair? Well, it's in the nitrogen column, so it should look the same way. Okay, so that's a very good hint to figure out those lone pairs. Okay. Anybody confused on that? Good, awesome. All right, let's go through A. So we know A is in 6 valence, and we know that it always likes 2 bonds and 2 lone pairs. So that's how I knew 2 lone pairs. So count areas of electron density. I see 4 areas. That's telling me sp3. But remember, always check for resonance. I could do resonance either to the left or to the right. And, let me just show that real quick. So the resulting structure would be, that, and maybe those 2 are prime, except for something else. So then, because now it's not 2 lone pairs and 2 bonds like it's supposed to, we end up developing a formal charge. Same thing for that oxygen over there. Okay, so if I were to count areas of electron density from here, I see I have 1 double bond, 1 sigma bond, and 1 lone pair. That's 3 total areas, so I should be thinking sp2. Okay. sp2 for the bond angle, always 120. And then for molecular geometry is going to be AX2E. So if anybody remembers what AX2E is, that is bent. Okay. If I were to ask for electron geometry, maybe I would say trigonal planar, because it always matches whatever that hybridization scheme is. All right. Let's go to B. So for B, we're looking specifically at the carbon of this, I can move this arrow, the carbon of that alkyne, okay? And that carbon has 2 areas of electron density. It has this 1 sigma bond and then this 1 triple bond. So that's sp, okay? sp is always 180, and that is AX2, and AX2 is linear. And again, electron geometry would also be linear in this case. Sometimes it matches, sometimes it doesn't. C, so C is nitrogen. We know it has 5 valence, so that means it has 1 lone pair there. And can it resonate? So yes, it can. It can resonate to the right and push these. And what would I do here? Look, just alluding. Would this be pi bond to pi bond or pi bond to lone pair? And somebody put that in the chat box. Somebody wants to say. All right.
Pi bond to lone pair.
Awesome. Yeah, it's pi bond and lone pair. That's just like something I'm going to always tell you guys to do to never get resonance wrong. Pi bond and lone pair. Just get that phrase in your head. Pi bond and lone pair, pi bond and lone pair, pi bond and lone pair. Okay, so the resulting structure is going to be something that looks like this. And I'm not drawing the rest of the molecule. I'm kind of just drawing this fragment. But you get the point. So we went from pi bond to lone pair, and we have this resulting structure. So we have 3 areas of electron density. That's telling me a sp2. That's 120-degree bond angle. And from molecular geometry, this is AX3. So that's trigonal planar. Same thing for electron geometry. It would also be trigonal planar for this case. All right, D. All right. Anions are a little difficult. People are like, I'm confused on what's going on. But just draw what that negative charge means. What that negative charge means is that there's already a hydrogen that you can't see, but there's also a negative charge on it. Okay, that's with the lone pairs present. So I see a total of 4 areas of electron density. I have those 3 bonds and that 1 lone pair. But that lone pair can resonate definitely over here and out. Okay, I'm not going to draw the resulting structure. It's kind of getting a little messy, but you can see they can resonate. So that would bring me down to 3 total areas. So this would be sp2, this would be 120, and this would be AX3. So trigonal planar and trigonal planar. Okay. Anybody have any questions on that stuff so far?
Can I ask a question about
Yeah, of course.
part C? Part C, molecule B, like that nitro group. Could you just like show how?
Wait, you said that backwards. Part C, molecule B. Are you talking
Sorry,
about?
like part C on the top, and then molecule B, the nitro group.
Oh, gotcha. You're over here.
Thank you.
Yep. So you want me to talk about that one?
Yeah. Could you just explain how it would like the charge, like those lone pairs on the nitro group would go out onto the oxygen? Because like when you write it out, wouldn't the oxygens have full octets already? Like how would there be room to put the lone pairs there?
So you're talking here, right?
Yeah.
Okay. So you right now in this current situation, that nitrogen, like this lone pair on that oxygen, could not just donate by itself. You could donate it only if you push something else out. So you're right. Everything has right now 8 valence electrons. Okay. Everything has 8 valence electrons. Everything is happy for the most part, except that for the nitrogen and the oxygen, it's not in the typical bonding pattern that you want it to be. Okay, so that's why you have these charges associated with it. So yes, you're right that these oxygens have all the electrons that they I guess have, but right now these 2 electrons are being shared by the nitrogen rather than exclusively on the nitrogen or the oxygen. So what happens is when I resonate, you're not really making the octet even more. You're just now exclusively putting these 2 electrons onto the oxygen. So now you have 2, 4, 6, 8 completely on that oxygen. Does that make sense? Or I'm sorry, 6 completely on this oxygen, whereas before there were 4 completely on the oxygen. It's just a matter of making them permanently there or kind of delocalized and possible of moving, if that makes sense.
Okay, thank you. But then you had to assume that oxygen, like there was already a double bond there and then the other oxygen had a negative charge.
Oh,
I was just confused because it didn't already show that there was the charges, like different charges on those oxygens.
Correct. Okay, yeah, good point. So something I told everybody from the beginning is knowing the nitro-Lewis structure is very important. It's just something you need to, that I would say to memorize, even though I hate saying that word. This is something you need to just know. Like there's a positive on the nitrogen, the negative on the oxygen. The reason why you don't have any charges here is because the positive and the negative in this condensed cancel out to 0. Okay, so you would have to know that the nitro is this. That's the only one that you would need to know, though.
Okay, thank you.
Yep. All right. I think there's some chat stuff going on. Hal, it looks like you got it. So that's awesome. Thank you.
Wait.
Is there a question?
Yeah. So then, is it sp2
For the nitrogen?
is B? Yeah. For B,
Yes.
Is that sp2?
Correct. Yep.
Okay.
sp2, 120, trigonal planar. If you guys care for that one. Let's see. Yes, so many people are joining. Could the lone pair for D resonance the other way? So we would use the word resonate, but that's okay. Resonate the other way for the problem we did together. Yes, exactly. I said you could resonate either way, and it doesn't matter what you would pick. You would still get the same answers. Okay, Roxana. And there's always resonance on the nitro group. Yes, there is. There's always resonance on the nitro group, and we're going to talk about how important that is in chapter 10. Yep, hope that answers all those questions. All right, let's move on to 2. So this question is, I try to put it in this biological context, and we could really throw you any molecule in the world, but these, the DNA nitrogenous bases are a great example of, aromatic molecules, and they're basically what aromatic means is it extensively can resonate. Okay, so that's why we use these, if you guys see these nucleotides a lot. And you guys need to ask yourself basically one question. It's really easy for these, is can I resonate? Okay, can I resonate? If yes, p orbital. If no, hybrid orbital. Done. That's it. That's how you get these questions right every time. Okay, so I'll catch you on examples if you didn't follow me. Okay, so we're gonna talk, are we just talking about nitrogen for this question? Yeah, just nitrogen. So let's just start here, okay? So we're looking at this lone pair. Can I resonate? Actually, I don't wanna start there. Let me start here and I'll explain why in a second. If I look at that nitrogen lone pair, can I resonate? Yes, I can. I can resonate to the right with that carbonyl and push that out. So if I said yes and I can move, it's P. That's it. Okay, let's look at this one. So there's this lone pair right here. Can I resonate in? Yes, I can resonate in and push that pi bond out and make it a lone pair. So yes, I can do that. P. Okay. All right, now we're over here. So something that is very, very bad, and I really hope that somebody can guess this right. You know, I always like to leave it open-ended before I tell you the answer. Why can this lone pair not resonate even though it looks like it can? I'll see if anybody knows this.
Because if you would resonate, it would create like 2 pi bonds, and then that would be an sp hybridized, and then it would be like 180. And if the molecule is like 8 molecules or less, you can't have 100.
Amazing. I love that. That was the best answer. And like, I hope, and I see you guys are writing it in the chat box as well. So in years past, they actually never told us that. We kind of just had to figure it out. Now I guess they teach it to you guys, which is awesome. But yeah, so that should make total sense. Once I resonate, you know, if I were to show that resonance structure, let me just kind of draw it over here. And I'll just draw like what 2, I think it's +2, 2 plus it becomes or something like that. Let me think. 5 valence minus 4 6. No, it's still plus, whatever. So once you get here, once you get to this structure, you see that it's 2 areas of electron density. That tells me SP, and we knew SP was 180-degree bond angles and it's linear. Well, there is no way that you can be linear in like a geometric shape like this. Like unless you're a line, like there's no way that you can form a 180-degree line in this structure. We don't ever have molecules that look like this. You know, that this sorry, I drew that wrong. It would be like equivalent to, I don't even know how to draw this. The fact that I can't even draw it tells you that that it doesn't exist, right? So you can't have these 2 pi bonds next to each other. So although it looks like it can resonate, it can't. So then we would just classify it based on the current hybridization. We see sp2. All right. So this lone pair can resonate. So that's P. And then this lone pair, it's the exact same situation where once I resonated in, I would get 2 pi bonds. So that would have to be sp2. And I think I just saw a question. Would the situation only occur if this is aromatic? No, no. You don't necessarily know what the criteria is for aromatic yet. So I'm thinking of like all these orgo-2 things that violate that. So yeah, no, that answer is no to that question, honestly. Aromatic is not interchangeable with resonance, okay? Just because something has resonance doesn't make it aromatic, okay? So maybe that explains it a little bit more. All right, B. So again, we'll try this one more time. I think it's pretty easy. So I see this lone pair right here on the nitrogen. It definitely can resonate to the right, so that would be a p orbital. I have this nitrogen over here, this lone pair. It can definitely resonate in and push that around, so yes, p. Over here, if I were to resonate that into the left, I would get that double bond situation again. So no, that would have to be sp2. Okay, are you guys kind of following this? I don't think I need to do any more unless someone's having issues with this. And there's also more examples of that in 3 and 4. All these questions are just more of those. So here's an example, like, so for that question, I think Lauren just asked, does everything have to be aromatic? So above 3, these are all aromatic molecules, but 4, these are not all aromatic molecules. Okay, and you still have that same, you know, considerations that you have to deal with. Okay. All right. So we're on the next topic in chapter 1. I think this is one of the last things we're going to talk about. Is with
Oh, I have a quick question on number 5.
Sure. Yeah. On number 5.
Or number 3. It's going to be your number 3.
Okay.
So it says furan.
Furan? Yeah.
Yeah. In the book answers, it said that it could be P or sp2, but in
Yes.
the lecture, she said it was sp3, so I'm just confused on how you would classify that.
Okay, so I think you're getting two structures confused. So furan is this polar solvent, but then there's also tetrahydrofuran. So it's tetrahydro, and tell me if I'm wrong, I don't know, tetrahydrofuran. I use this solvent a lot in my lab, but these would be sp3 because no resonance is possible because you already have all the hydrogens here. There's no pi bonds to push out. So those would be sp3 orbitals. But here we can resonate. So one would be a P and one would be sp2. Does that make sense?
Okay.
Or am I
That,
was
no,
that
that
it?
makes sense.
Yeah. So you might be getting confused with the two molecules. This is the tetra version. That's just the aromatic version. But yeah. Okay. And
Thank
also, yeah, along this line of P versus sp2, it doesn't matter which one you said was P or sp2. As long as you said one was P and one was sp2, you get full credit.
Hey, can you explain that sp2 and P thing?
Yeah, sure. Yeah. It's so funny. I know your voice, Emily. It's awesome. All right. So I'll try it with thiophene. Okay. So that would be this middle one, and it's going to give you the same situation. So you can see one of these lone pairs can definitely resonate, you know, and form this resulting structure. Actually, let me just draw it over here. Okay, so that would be the resulting structure. This pi bond, you know, that forms this positive charge in the sulfur, and everything else is fine. We have that lone pair on that carbon, and that's fine. So the fact that I did that move, that tells me that whatever lone pair I just pushed was a p orbital. Okay, so p. But then now that I have this one, what happens to this? What happens to that lone pair? Well, that lone pair can't move in for reasons we just talked about. Yes, in theory it could resonate. It has all the conditions necessary. But we talked about that one thing that prevents it, and we need that 180-degree bond angle, and you can't have that 180 in a ring like that. So this one, if it can't move, is going to be sp2. So you can say the other one is sp2. It doesn't matter which one you say, either the left or the right is p or sp2, but you have to say one of them is p and one of them is sp2.
Okay, that makes sense. Thanks.
Cool. Yep. All right. Let's do these bond overlaps. So this is just an extension of what we've done already. It's not any more difficult or less difficult than the stuff that we've already talked about. So let's just talk about, so the first structure is actually one of your main biologically active amino acids in your body. This is arginine, if anybody recognizes that. Arginine. Cool. And arginine, let's talk about A. So in that bond, in this bond between the carbon and the nitrogen, we have to basically talk about what orbitals are overlapping to form that bond. And we talked about this. I don't know if you remember when I was showing what methane looks like. So this would be methane, CH4, so CH, H. And we're like, what does this really translate to? And what it translated to was I'm just doing this really quick. And all of these lobular things are carbon sp3 hybrid orbitals, okay? So, you know, if I were to point to, let's say, that bond and call it A, what orbitals overlap or physically touch to form that bond? Well, we would say for that bond A, it would be the carbon sp3 overlapping with a hydrogen 1s orbital. So that's kind of the logic that we're talking about now, okay? So I hope that makes some sense. Let's just jump into these problems. So for A, we would classify the hybridization of that carbon. We see that there are 3 areas of electron density around it. So that would be sp2. That's how I got that first thing. And then for nitrogen, same thing. I would see I have this one double bond, this one single bond, and that one lone pair. So that tells me nitrogen sp2. Okay, cool. And we talked about how those extra p orbitals help to form those pi bonds. So again, maybe if this wasn't necessarily clear, let me take the example of ethene. Okay, so ethene is C2H4, and it has this structure. Let's do this really quickly. Ethene looks like that. And you know, when we're drawing these, so these are all carbon sp2 orbitals. And again, remember, these are all the hydrogen 1s, and I'm just going to draw circles, hydrogen 1s. But then remember, we talked about the whole energy diagram and how they blend and whatever, but what we have left over are these unhybridized p orbitals. And it's the electrons that are left in those unhybridized p orbitals that can form extra bonds in addition to that sigma bond. And this is now our pi bond. So pi, pi, comes from these p orbitals, and these sigma bonds come from these like hybrid orbitals. All right, so that should give you a little bit more insight. And then we can look and see, so that extra p orbital, if it's applicable, would just be a result of these two p orbitals overlapping. Now, it doesn't matter if I say x, y, or z, as long as they are the same. And why is that true? Well, that makes sense. You need your orbitals to be in the proper geometry in 3D space, like in the x orientation or the y orientation or the z orientation, to overlap. Because what if I had one, I guess, coming out in the y? The y would be this way. That x, which is 90 degrees up, can't match with this y 90 degrees like forward coming out of the page at me. So you just have to have the same orientation. Doesn't matter what letter, but as long as that they are consistent. Okay, so that's where I got these. And let's just jump into problems. I think that's enough talking about that stuff. I think we have some questions here. Will the situation only occur if the most, oh, say that one, do we need to take hybridization into account when writing? Yes, we do. Yes, we do. Yes, we do. Juliana, I'm going to catch you on one of these problems coming up. All right. So for A, it's a perfect example of what you just talked about. So we have a lone pair on that nitrogen. Can it resonate? Yes, it can resonate. But what this question asks, and it's very common for people to mistake this, is we are asking in the exact fashion that it is right now, what is the bonding pattern? Okay, and I know that can be confusing based on the answer I'm going to give you. So we are looking right now at this sigma bond. So our answer should only have a sigma bond. Okay, we're not going to talk about a pi bond. However, you might be thinking to yourself, yeah, when I resonate this and I push those electrons out, I get, and I'm just going to draw it like this, I get a pi bond now. You see that? How I kind of formed this pi bond? This is the resulting structure. Once I push those electrons down, I form this pi bond. That doesn't mean I report that pi bond, okay? You need to think about resonance so that you can understand the hybridization of this nitrogen, okay? So by doing this, I have now realized that that nitrogen is sp2, okay? Okay, and then that carbon is also sp2, okay? But there is no pi bond to report, okay? Don't write a pi bond because there wasn't one in the beginning structure, okay? So that's it for this guy. Okay, B. I know this might be a little weird, but just keep going with me. So for B, there's this one lone pair that you don't see here. Okay, so right now nitrogen is already in its sp2 structure where we can't go lower for reasons we talked about. We can't resonate those lone pairs in again because we would have that 180-degree argument. So right now we're already at sp2 for nitrogen. Okay, and that carbon is also already sp2 and we can't go any lower. So that would also be sp2. But in this current structure that I see on my paper, there was a sigma and a pi bond. So I better also report that pi bond. So that pi bond is going to be carbon 2px with carbon 2px. You could have said carbon 2py and nitrogen 2py, or carbon 2pz and nitrogen 2pz. But as long as you have the same electron arrangement and orbital arrangement, you guys would be fine. Correct. Does not matter which one you write first. You could write carbon first, nitrogen first, whatever. Which carbon are we using? The carbon in this carbon-nitrogen double bond for B. That's the one we're looking at. All right. Emily, did that clear that up for you? It's the carbon of this B bond. Cool. Anybody else so far? All right, we're good. Let's jump to C. Okay, so C, we have this carbon-oxygen bond, okay? And can these lone pairs in that oxygen resonate anywhere? And the answer is no. I don't see any other like pi electrons. Great answer in the chat box. There are no areas for us to resonate. So that tells me that those lone pairs are in sp3 orbitals, and all of those orbitals around oxygen are going to be sp3. So oxygen is sp3. Okay, so let's look at that carbon. Can this carbon have any sort of alternate resonance forms? No. So that carbon is also sp3. And if we use all of our orbitals, remember what sp3 meant, we're using all of those atomic orbitals, we don't have any left over. So there is no possibility to make a pi bond, and there also wasn't a pi bond depicted. So there's that. D. So D is this alcohol. We know it has 2 lone pairs. Can it resonate? No, it can't. So that oxygen is going to be sp3, and that hydrogen is going to be 1s. We talked about why hydrogen is 1s. It only has 1 atomic orbital in the 1s, and it has 1 electron, so it can't even hybridize in the first place. Okay, and then none here. All right, so I think that was just an extension of what you guys already know with hybridization. Does anybody really want me to do another example of that? Or
Yes.
can we, one more? All right,
Yeah.
let's do one more. All right, so for A, again, let's draw on any lone pairs that aren't here. So we have this nitrogen lone pair. The carbon is already sp2, okay? And that nitrogen right now looks sp3, but you can tell it can definitely resonate to the right or to the left, it doesn't matter. But either way, it can resonate, so we know we're gonna get not 4 areas, but really 3 areas, okay? So that tells me that the nitrogen as well is sp2, okay? Was there a pi bond shown? No, so don't write it, even though you do technically form one when you resonate. And I think I got a question, let's see. So even if there's a possibility to make a pi bond through resonance, we don't list it exactly. Claudia, everybody read Claudia's message. That's the big take home point I'm trying to communicate to you guys. Is that so even if there's the possibility to make a pi bond in one of these resonance structures, these contributing structures, we're not gonna write it for this specific question, okay? Because there is no pi bond. Like you can, what resonance tells you, you know, obviously, is that arguably there are other structures that exist with partial character. So yeah, you can argue in real life that this carbon-nitrogen bond has some double bond character. But in this current structure, I did not show you a pi bond, so you better not write one. Hopefully that helps you guys. All right, so that's A. B, again, same situation with this nitrogen. I have this lone pair here. This carbon is already in the sp2. I can't get lower than that. But this nitrogen can definitely resonate either to the right or to the left. So that makes nitrogen sp2. Same situation. I don't have a pi bond drawn in already, even though I formed one in the resonance contributing structure. So I'm not going to write it. C, so we have these lone pairs on this alcohol. This is kind of a repeat of what we did above. There is no hybridization, no resonance possible with these lone pairs because we're all sigma bonds here. So this oxygen would be oxygen sp3, and that hydrogen would be a 1s, again, for reasons we talked about. And D, so D, we're talking about this carbonyl bond. So this is important because we're going to talk about this a lot, in Orgo 2. But this carbonyl is this carbon sp2, like we talked about, and this oxygen is also sp2. We can't get lower than that, okay? But there is a pi bond already shown. So that's what I need to write right here. So let's, for this example, write 2pz and oxygen 2pz. I'm literally just picking Z for fun. It has nothing to do with any reason. And that's how I do those. All right, for fun. You guys get me. Seriously, I don't think Orgo is so crazy and intense. I hope you guys don't think it's so crazy and intense, like so far. It's pretty self-explanatory. All right. Anybody else? Anybody have any questions for this? All right, let's keep moving. All right, this has been a topic. It's the so far for me. That's fine. You'll see. You guys will see. All right, so organic bonds. So this is like sometimes some people, I think in the summer said that they didn't even talk about this. I'm just going to talk about it for a brief second because it's like literally a no-brainer. On the test, if we were to ask you any of these questions, you are going to get the Pauling scale of exactly. You're going to get the Pauling scale of electronegativity table given to you on the test on Canvas. So there's no reason to memorize any numbers or anything like that. God bless, exactly. So you guys do not need to worry about memorizing any numbers. It's amazing. So all those numbers will be given to you. So literally what you do is you take the higher number. So for, in this case, it was oxygen, which was 3.5 on the table. Silicon, lower number, 1.8. Subtract those values, you get 1.7. Did 1.7 fall in any of these categories? This is what you memorize. I hate to say it, hate that word. This is memorizing. So just know less than 0.5 is nonpolar. In between those two values, 0.5 and 1.9 is polar, and then anything higher than 1.9 is ionic. Note this equal sign. It like trips people up every time. Once you're over 1.9, you're ionic, okay? So you know you don't get a calculator. I think you guys can subtract these two numbers in your head, hopefully, pretty well. They're just, you know, tenths place decimals. So yeah, so no, you will not get a calculator, but you'd be surprised. Yeah, you won't get a calculator, but you'll get a Pauling scale electronegativity. So you just subtract these two numbers, find out where it fall into these ranges, and then you classify them as such, okay? So, yeah. I don't know. I'm just going to leave it there. I'm not even going to do these. So that's that. All right. So for dipoles, this is important. So some of you guys, I know, I hate physics. I literally hate physics. It's the worst thing. I'm in a class called physical chemistry right now. So it's the physics of chemistry, and it's the worst. But this is the one physics thing that might help you here if you know some physics in terms of like vectors and dipole moments. So essentially, we know what polar bonds are. I hope you guys know what polar bonds are. And that just means an unequal sharing of electrons in a bond. And that just has to deal with, you know, the amount of protons in these atoms, you know, effective nuclear charge. These are all things you learned back in Gen Chem, and I'll just briefly talk about it again. As you go left to right on the periodic table, you're increasing, you know, your atomic number. What does atomic number refer to? Well, it refers to the protons, the number of protons in your atoms. So as you're increasing the number of protons, you increase the number of positive charge in your nucleus, which means those electrons in the outside shells are really, really attracted to that nucleus because you have a bigger positive charge in your nucleus. So that's really the concept of, you know, this polarity, why some atoms pull more than others. It's because they have more protons, you know, which want more electrons more. Okay, so look at this example. So clearly, out of nitrogen or fluorine, you know, and we know the trend is top right. So top right is the best up here, okay? So if out of nitrogen and fluorine, we see that we have fluorine all the way to the right and nitrogen's over here. So since fluorine is closer to the top right, it's more electronegative. So we should just draw lines spatially in all 4 directions. Okay, but since they're all pointing equally in 3D space at these 109.5 bond angles, they all kind of cancel out vectorally. Yeah, vectorally. So if you don't believe me, let's just do head to tail. So if I take this vector and I'm going to put this tail of this vector here, and then I'm going to put this tail of this vector here, and, you know, in theory, I would have drawn these in line, but you see how once we form this complete structure of putting all those lines together, we're back to where we started. So a net zero dipole moment. Okay, so nothing. Okay, so for A, out of fluorine and chlorine, which one is stronger? Well, fluorine has a bigger pull. So we're going to write these lines here. Okay, and then if I were to do the vector thing, my resultant would just be this. So a net dipole moment in the red. That's the answer. Is anybody confused on what I'm talking about head to tail, like vectors? I assume you guys know what vectors are at this point, but I might be wrong. Okay, I'm hoping that's good. All right, so for between the hydrogen and the nitrogen, all of these dipole moments are going to be forced this way towards the nitrogen. Okay, and you can kind of see, you know, what happens when I push, I guess, pictorially, I guess that's the right word, and I guess you would say that. So from head to tail, if I were to add all those together, it'd be directly up. Since F is stronger than chlorine. Okay, Lauren, great question. Lauren, you have great questions. Okay, let's go back to A for a second. So read Lauren's question for a second, and it was saying, since fluorine is stronger than chlorine, you don't take into account the dipole area of the chlorine. I am taking into account the dipole moment of the chlorine. However, if I were to really like have numbers to this, let's say it was like 3 newtons down here. Let's say this was 3 newtons, and let's say this one's 5 newtons. I'm just literally skipping this and writing 2 newtons. It makes it simpler for me. There are dipole moments going down. That is totally, I'm not saying that there aren't, but I'm just kind of already skipping that and telling you just focus on the ones that are the most electronegative. But yeah, great question. Caroline, can you explain how you're putting the vector arrows? Head to tail? Yeah, so it's something called head to tail. If you haven't had physics, that's where it comes from. And what I'm doing is this is the head where the arrow is, and then the tail is obviously the tail end of it. And what you do is you take the head of one of them and you put it to the tail of another one. So that's what I did right here. So let's call this vector line A and vector line B. This was vector A and that was vector B. So the head of A was put at the tail of B. And you kind of just connect them all together. Okay, and that's kind of how I do that. Okay, so for C, oxygen is more electronegative than carbon, so we have a dipole moment up. It's the only dipole, so there we are. Okay, so fluorine and chlorine. So we have, out of fluorine, so let's just do this. The chlorine that pulls this way is going to cancel out the chlorine that pulls in the same magnitude but opposite direction that way. So I can ignore these, that's 0. And the same thing for fluorine is true. If I pull enough fluorine, let's say 5 newtons upwards, I'm gonna pull 5 newtons downward as well. So those cancel. So none. Do you see that? Hopefully. Okay, so for E, so we have bromine this way, bromine this way, bromine this way. This one is kind of hard to see. I don't know if any of you guys know, like, if anyone knows about dreidels or tops or like, spinning tops, anything like that. If you were to pick it up from like the little wooden piece or the little plastic piece, whatever, where you're supposed to spin it, and you were to like kind of pull that over, like look up into the ceiling and pull that dreidel above your head or that top above your head. And you can see that there'd be like these like arrows all kind of pointing out downwards at your face, kind of like a pyramid almost, okay? I don't think, so, this is a question. Oh, okay, that was a question, sorry. So you get all these arrows kind of pointing out at you like a pyramid almost. So it kind of like looks like this. I'm gonna draw this in a wedge so you see, and like that. So they're all kind of pointing downwards. So if those were to add together, it would be one dipole moment directly down, like down into the page. Okay, that was a little bit harder to see. And if you don't really understand me, this is what I did. So if I put all those arrows together, head to tail, you get one dipole going down. Okay, pH. So we kind of talked about this. What does pH mean? Well, pH is phenyl. We talked about phenyl, and phenyl is just code word for this. Okay, so this whole molecule is carbons and hydrogens, so no dipole. Okay, there's no drastic difference in electronegativity that is going to have a dipole moment here. Okay, so for G, we have a dipole moment towards the oxygen, a dipole moment towards this oxygen, a dipole moment to that oxygen. And if you were to add them all together, you get 0. And I think someone asked for F again. Yes, I can explain F. Okay, so it doesn't matter that this is a negative charge or that this has double bonds. We're just looking at qualitatively the identity of these atoms. Okay, and yes, for F. So for F, phenyl is just carbons and hydrogens. And if you look on the Pauling scale, I don't have it pulled up, but I can just do a quick Google search. Hold on one second. Pauling scale of electronegativity. All right, so carbon on the Pauling scale is going to be 2.55, and hydrogen is 2.20. Okay, so if you were to subtract the two of those, you're getting like 0.35 of a difference in electronegativity. That is like way below the nonpolar region, okay? So all carbon and hydrogen bonds are gonna be extremely, extremely nonpolar. And I proved that by using those values, all right? So for G, we have a localized dipole moment towards this chlorine. We have another localized dipole moment towards that chlorine. You can do vector addition, head to tail, and you draw the resultant, and you can just do that. But honestly, some of you guys might be really good at this point and just see like, boom. That's what I do, but up to you guys. And for this one, same thing. Boom, I just see one fluorine going up, that's it. So you'll get better. Trust your gut with these, honestly. Like if you have a feeling you know where it goes, it's probably where it goes. All right, and that's dipole moments. All right, the last concept of chapter 1, and like I guess the most difficult or most tested one, is going to be resonance theory. So we kind of already talked about this all together. We didn't really talk about major contributor though. So we'll talk about those criteria and then we'll finish. I think we're doing pretty good with timing and stuff like that. All right, anybody have any questions up until this point on hybridization theory, formal charges, dipoles, types of bonding, anything like that? Great. All right, so let's talk about resonance. So we talked about these problems already. One more time. So we have some criteria that I gave you. So for you new people that are joining this session and were in last week's, what we talked about were Stevens' rules for success when doing resonance, right? And we talked about these things. Number 1, if there is a carbonyl, so this carbon-oxygen double bond, it is a very, very good sign that you want to start by resonating those lone pairs out. Those pi electrons out as a lone pair, okay? That's just a very obvious trick that I'm gonna tell you guys off the bat. 2, always do one move at a time unless you exceed the octet. So that's what I'm doing here. I'm just doing one arrow at a time, unless there's some sort of octet issue, which we have not seen yet on this page. Then, when given the choice in a cyclic system, okay, it's best to do pi bond to lone pair, then pi bond to pi bond. And I know that may not make sense, but we'll see an example of that. And I'm trying to think, is there any more that I'm missing? I think that's it, the 3 rules. Okay, so that's that. And major contributor. So what does resonance theory mean? And it's actually really interesting. So ozone is the perfect example of this. Oh, my connection cut out. Kelsey, you say 3 rules again. Aha, yes, I could say these again. So real quick, one more time. If there's a carbonyl, start with those pi electrons in that and resonate those out. First thing. Step 2, source to sink. So always a source of electrons going into a sink, so some sort of deficiency, okay? I guess there are 4 rules. Do one move at a time, okay? Unless you exceed an octet, so notice there's only one arrow at a time. And then finally, when given the choice in cyclic systems, always go pi bond to lone pair, not pi bond to pi bond, and that will make sense in a second. So what resonance theory is, and ozone gas is the best example of that, is there really is no one true structure of these molecules. They're really a blend of all of these together. So, structure A, structure B, and structure C are all possible. They all technically exist in real life. And, basically how we know this is if you look in your textbook, it's like the one thing that it's actually useful for. I could actually pull that out for you guys here. This is great. Resonance. Give me 1 second, I'll pull up the page. 1 sec. How do we know that? So like the perfect example would be this. Do you recommend reading? Absolutely not. Do not read that book at all. Do not. The reason why I wrote this workbook is because the book doesn't do a good job. Yes. Just do the workbook. That's it. That's all you do. The workbook, watch lecture videos, and do what I tell you. That's it. Yes, T. All right. So we have this carbonyl, right? This is a ball and stick model of formaldehyde. Okay. So we have these 2 hydrogens right here. The black ball is a carbon, and the red ball is going to be an oxygen. Okay. So this is literally just carbon, oxygen double bonded, and the 2 hydrogens. Okay. Real easy. And what this map shows is the more red you are, the darker those tones are, the more negatively charged. Whereas the more blue or the more lighter tone or cooler tone colors indicate positive charges, okay? So, in this structure, we don't have a formal negative formal charge on that oxygen atom, do we? No, it's just regular formaldehyde. So that actually looks like, hold on, let me move over. This is B, the exact structure of B, if you guys are looking at it. That vector map, or what I just showed you, or all those colors, is this structure. So notice there is no negative charge on it yet. But why does this, graphical map show this red negative region on top? And that's because one of the resonance contributors has a full negative formal charge on the oxygen. So that's kind of what resonance really means. It's like you have all these other structures possible that really kind of form this blend of the true picture of what that structure is. That's kind of the theory. That's all you need to know for that. All right, let's do some problems. All right, let's do D. So for D, we see that we have 2 other structures present. Okay, so Stephen's rule. When I see a carbonyl, it's a good place to start there. So let's just do those arrows, 1 move at a time. So let's draw the remaining skeletal structure the way that it is. And now I have, instead of those 2 lone pairs, I have 3. So that forms a negative charge there. I took electrons away from that carbon, so that forms a positive charge there. If you're confused on the charges, all I am doing is applying the formal charge formula. You are going to get so good at just knowing electrons away, positive, electrons on, negative. Like you'll know exactly what a nitrogen positive charge looks like. You'll get there. So if you're a little slower now, don't worry. The next move is source to sink, okay? So we have another source of electrons I haven't touched yet, so on these nitrogens, and it's going to dump into a sink or some sort of deficient species, so that carbocation. This carbocation only has 6 valence electrons, 2, 4, 6. So let's put that source into that sink. And here we go. And that's the structure. All right. So these are my alternate resonance structures. If you follow my rules and my guidelines, all of you guys will be consistent in getting these structures. Okay. So now how do I determine which one is the major contributor? So like I said, you can have multiple different types of structures and they all kind of blend together to form this conglomerate or this true picture of the molecule. But if anybody has read Fault in Our Stars, if anybody has seen that movie or know, like, you don't even have to know the movie or watch it to know this kind of famous line. They say some infinities are bigger than other infinities, right? I hope some of you guys know what I'm talking about. Some infinities, oh, wow, way to just like do that to all of us. Yeah. So, so some infinities are bigger than other infinities, and the same kind of logic can be applied to this resonance problem. Some contributing structures are bigger or better than other contributing structures. And that's the logic of what a major contributor is, okay? So I always like to say, some infinities are bigger than other infinities. Think about that logic with resonance, okay? So there's gonna be one structure here that is more stable, that contributes more to the overall picture of what that molecule really is. And the criteria is as follows. 1, preserve your octets. And I'm gonna write this really fast. Preserve the octets. That analogy just made so much sense. Yay, I'm happy. Yay. That's the whole goal of these office hours, to just break it down. As long as you learn Orgo right, you guys will be fine. All right, preserve octets. So number 2, we want to minimize our formal charges. Okay, what does that mean? And 3, we want to minimize charge separation. And 4 is that, I guess I'll just say negative charge on most En atom. I know that's like really gross and kind of like concise, but that's really all you need to know. Number 1, in that order as well. Number 1, preserve those octets. 2, minimize your formal charges overall. 3, minimize, if you have formal charges, minimize the separation between them. And 4, the negative charge has to be on the most electronegative atom. So I know I'm running out of time, but I promise you I'll be like 2 or 3 more minutes, so just stick with me. So let's run through that criteria real quick. So out of all 3 of these structures, is any of them missing an octet somewhere? Well, look at that middle structure. That carbocation is electron deficient, and that's a big sign. If you see a positive charge, double check to make sure that you have your octets figured out. And you don't here. You only have 2, 4, and 6 electrons. So that immediately rules this structure out as being like the major contributor because it doesn't have all octets. That's not a stable thing. 2, we want to minimize our formal charges. And why is that? Well, if anybody knows anything about the weather or anybody knows anything about me, I really, really like the weather. I think it's really cool. It's just changing every day. But something that's really interesting is that the lightning in the sky forms from a buildup of negative charges. There's a lot of electrons in the clouds, a lot of negative charges. And because it is so, I guess, massively charged and negative, what happens is this huge discharge of lightning just will shoot down to the ground. And in that lightning bolt, those negative electrons are traveling and literally get attracted to the positive ground and then dissipate and spread out. So it's kind of this natural way of returning charge back to the ground. So the reason why I talk about this is nature kind of like mimics itself in the sense that lightning hates negative charges. That's why we have that massive loud clap. Nature hates these negative charges. The same thing in molecules. Molecules hate to be charged, okay? The fact that they're charged means that there's an unideal bonding pattern. It means that there's an associated reactivity to it. So that's why we want to minimize these formal charges. So based on that criteria, this first structure doesn't have any formal charges, whereas this one has 2 formal charges. So that rules out this one. Boom, I'm done. That's my major contributor. Okay, so yes, that's where we're at. Let's do G, and then I'll leave you guys. Okay, so this is a rank example. So real quick, on G we have this lone pair. So the first thing I want to do is resonate those lone pairs in. So 1 move at a time from source to sink, unless I exceed the octet. Well, I definitely exceed the octet at that carbon. I have 2, 4, 6, 8 electrons already there. So this is that really, really key rule. When given the choice in a cyclic system, do pi bond to lone pair, not pi bond to pi bond. So here, I want to do pi bond to lone pair, okay? So the reason, I'll tell you the reason in a second, but you guys will get this structure. Okay, so we're here. And then what you want to do is just keep pushing around the ring. So this source goes in, and then now we're going to form a lone pair there. So the resulting structure is going to be that. Okay, and then after that, you keep pushing around. So we have this structure, and then you have one more to go, and you are here. Okay, so these are my 4 other structures, okay? But what would happen, and I'm gonna do this in black, and this is, I'll end here, is if I were to push these in and then do pi bond to pi bond, so instead of at that corner, I'm putting it here, then I exceed the octet here. So then I have to push those in. And then I exceed the octet here, so then I have to push those in. And then the results of all of those resonance arrows, which this isn't wrong, but it's just gonna get you points off on your test because you're missing structures. What happens is if you don't listen to me and do pi bond to lone pair, you're going to skip this structure, and this structure, and you're gonna go right to that final product. So that's why you do that rule, pi bond to lone pair, so you don't skip this one, this one, and this one. All right, and I will leave you at that, and I will see you guys on Wednesday, and we're gonna talk about chapter 4 stuff. All right, good luck, guys.
Thank you.
Yep.
Thank you.
Yes, yes, yes.
So Steven, next time we're just gonna do chapter 2.
It's chapter 2 in the student workbook, but chapter 4 in terms of your class. Yeah.
Okay, thank you.
Yep. See ya.
Hey, can I quickly ask you about F?
Yeah, of course.
So don't we have to do, or at least like on the answer key too, like it showed a pi bond to pi bond movement. So I would like, yeah.
On the key? Let me pull it up on Canvas real quick and I'll look at what you're saying. Stop